Welcome everyone to the Spectral Geometry and the Cloud seminar. Today we have the pleasure of having Ari Laptev, who will speak about spectral inequalities for Jacobi matrices following Hundertmark and Simon. Ari, the floor is yours.
Okay, thank you very much. What we have done, it's sort of it's a project we started quite some time ago when Michael visited me at the Institute Monotonicity Lemma. And then, so let me just begin. It's about sort of some kind of a proof of conjecture, which was in the paper of Hundertmark and Simon in the paper which they published in 2002. And it's about sort of Lieb-Thirring inequalities for the spectrum of Jacobi matrices. So let me just start with the following. So let's look at the standard Jacobi matrix, and we denote it by G. This is a J, and then it looks more or less like this. So what we have is that we denote the Jacobi matrix J by using this notation, which actually was introduced already in the paper of Hundertmark and Simon. So what we assume is that n converges to 1 as n go to plus or minus infinity, and in such a way so that the spectrum, there is a sort of a simply continuous spectrum between -2 and 2. This is kind of a standard thing, you know. I mean, if you take non-perturbed Jacobi matrices and all these A's, an are equal to 1, then you have a sort of unperturbed discrete second derivative. So if b is equal to 1, so then that's what we have. If all a and converge equal to 1, then we have just second derivative. And of course, you get it, I mean, because simply, and if you take Fourier Transform, so that you have un would be coefficient of a function on the interval, say, minus pi, then the symbol would be cosine, 2 cosines. So this is sort of a standard setting of Jacobi matrices. And then let's denote by E plus and E minus. This is the eigenvalues of Jacobi matrices, that it's larger than 2 and smaller than -2. So what we do is that if we perturb the Jacobi matrix by not having a and identically equal to 1, and then we have also diagonal Bn, which is sort of supposed to be potential, and then the eigenvalues might appear under certain condition of decay, of course, an and bn. And in fact, the statement which we have here, it's exactly describe exactly conditions on bn and an, so that you have eigenvalues satisfying the following properties. So if we look at this formula a little bit closer, then say, for example, again, if an identically equal to 1, then we simply have discrete Schrödinger operator, then this term doesn't exist naturally. And if, again, if they all equal to identically 1, and if bn, for example, are positive, then we don't have anything which drags the spectrum from the point -2, to the discrete part, to the sort of -infinity -2 part of the spectral semi-axis, and then we only have positive eigenvalues which are greater or equal than 2, or greater than 2. So now, so why is this inequality could be identified with a so-called Lieb-Thirring inequality in the discrete setting? Because the following. So if we look at the elementary identity here, then we see that, for example, E plus 2, of course, it's greater than 4, greater or equal than 4. So we put here 4, and then also, since we take modular, respective A minus, E minus -2 is also would be less than -2. So we have this inequality. And since we take square roots here, and we consider square roots here, then what we can do, we can, using this inequality, we can rewrite the above inequality in the following way. And then what appears, it's 1/2 appears here. And the claim here that 1/2 is sharp, well, speaking about this part, we shall discuss it a little bit later, but if at least an, all an are equal to identically 1, then this inequality is sharp, and then we get exactly 1/2. It's a sharp constant. So let me just describe. Of course, one can also know here that the inequality which we have here, it's slightly better than the inequality we have here, because here we have simply the inequality. We use this inequality, and we might lose something here, of course. Anyway, so what is this here? We have a distance between the positive eigenvalues, which are greater than 2, and then the spectral point 2. And here we have the distance between the negative eigenvalues, which are below -2, and the point -2. That's what it is. So let's discuss a little bit the situation with this 1/2. So it actually corresponds to the case, the continuous case. So what I want to say, if we consider Schrödinger operator on the line, say minus second derivative minus v is equal to, say, minus lambda u, so spectral problem, then respective, so v is a potential which plays a role of b in the continuous case. The Jacobi matrices degenerated, just we have only second derivative. We don't have any coefficients in front of the second derivative involved in the second derivative. So so it corresponds to the case when a and are equal to 1. And therefore, so what we have is that there was this inequality proved by Hundertmark, Lieb and Thomas, Larry Thomas, who sort of had this sharp constant 1/2, and it is achieved. So indeed, what we do here, if we assume that v is equal to simply a delta function, then delta potential generates one negative eigenvalue. It's very easy to compute it. So how do we do it? We just, yeah, the eigenvalue is actually equal to exactly negative eigenvalues minus lambda is equal to -1/2. So it's very easy to see that this is an eigenfunction, the only eigenfunction we have, and then simply if we take the second derivative, after taking first derivative, we have sine of x times e to the power minus x modulo x divided by 2. We derive again, sine x generates 2. If we take derivative, 2 delta functions, and then 1/2 would be delta function here exactly. And then again, if we derive the exponential function, we get this one. So because we get sine x squared. And if you look at what happens here, then this part crosses it out with this part, and then we get exactly the eigenvalue minus lambda is equal to -2. So this is a sharp inequality. Right. Now, similarly, it's true also that the inequality which we had also, it's also sharp. So what do we do here is the following. So suppose, let's consider the first example. I mean, this is a inequality which was proved by Hundertmark and Simon. So if you take example 1, and then all an identically equal to 1, and then assume that mu is strictly less than 1. So we introduce Bn, which look as follows. So so what is easy to see that the eigenvalue here with the so what we have is that all Bn are equal to 0, so no perturbation apart from the, say, for example, that when n is equal to 0, we have non-trivial value of b. If Bn, so I mean, it's very easy to see if E is equal to mu plus, I mean, and that's what it is, and the eigenvalue is equal to mu plus mu to the power -1. First of all, it's greater than 2. And secondly, so of course, if you substitute here E and then compute a little bit, then that's exactly what we have, this identity. And then clearly what we have here is that this value, 1/2, yeah, exactly. So this value, which we have here, is equal to identically B. So that's exactly what we have here. So it's actually what we can write here. It's a B0, right? So when an identically equal to 1, we have very simple example which shows that this inequality is sharp. And let's consider another example where all Bn identically equal to 0. A little bit more complicated. So what we have here now is that now instead of having eigenvalues, we should consider perturbation of An, and it's again a very simple perturbation of a standard An compared with the free discrete Schrodinger operator. So almost all An equal to 1. But when n is equal to 0, then we have A0 is equal to A, which is greater than 1. Okay, so then what one can easily see is that the matrix J has 2 eigenvalues, and then a positive and negative, and they are equal to this value simply. Again, if we compute the square root of E squared, or whatever, plus or minus, it is minus 4, then we get this expression. Again, it's a very similar expression to what we had in the previous slide. And then since we have 2 eigenvalues, one negative and one positive, then we, when we put here, then we have to write 2 here, right? And then we have 2a minus a to the power minus 1. It's not exactly what we have on the right-hand side here, right? Even if a0 is equal or greater than 1, right? But still, it's not exactly the same. But let's notice the following fact, that we can write down a minus a to the power minus 1 as a product of these two. So here we have a minus 1. And here we have something else. We have 1 plus a to the power minus 1. And again, it's not, of course, it's not the same as this expression, but if a is very small, if this small, I mean, small compared with 1, say if a is very close to 1, then 1 plus a to the power minus 1 converges to 2. And therefore, here this term is equal to 2, I mean, almost equal to 2. So this 4, which appears in this inequality, is not unreasonable. It's not unreasonable, and that's what we have. It's important to make a remark that if one can try to cook up something like this for a0 less than 1, and it doesn't work. And there was a suspicion that that it's actually this constant an that are less than 1 don't contribute in the spectrum. So, for example, here if you see in the right-hand side of the formula inequality of Hundertmark and Simon, an allowed to be greater than 1 or less than 1, and it still would be a non-trivial contribution. So there was a conjecture by Hundertmark and Simon saying that actually in this inequality, instead of writing modulo an minus 1, you can write an minus 1 plus, namely this is a positive part. So basically that means that the an which are below 1 don't contribute in the formula in this inequality. And that's what we are going to deal with. That's what we are going to prove. So the main result of the paper is this inequality that indeed instead of modulo an minus 1, we can put an minus 1 plus. So that is the contribution. Now, there is another contribution because the proof of Hundertmark and Simon, it went sort of not in a very, from my point of view, not in a very pretty way. And then there was and it sort of followed the original proof of Hundertmark, Lieb and Thomas. Then there was a later paper by Hundertmark, myself, and Timo Weidl, where we wrote a different proof of the same inequality, which is, from my point of view, it's very elegant. And that's sort of also what I'm going to demonstrate here, that in fact it works here too. And also it's kind of another example of how this elegant proof, which we had this in the paper of Hundertmark, myself, and Thomas and Timo Weidl, that sort of works here too, because obviously I think they tried. I don't know, but I suspect that they tried it and they couldn't succeed it. But here we shall present it. Now let's go on into the proof. So the first part of the proof is a standard. It's exactly how Dirk and Barry did it. So, well, for that, first we just introduce these notations. For me, it's convenient to split the matrix J into two parts, which A is responsible for the OF, the off-diagonal elements, and this is diagonal elements. So this is natural notation. A very important role is going to play matrix A1, and A1 is a matrix where all the off-diagonal elements equal to 1. So it basically corresponds to the discrete Schrodinger operator. So what one does is that basically one try to first reduce the problem to the discrete Schrodinger operator. And of course, on the way, when you do it, then some extra diagonal terms appear, and then and that's exactly why finally this formula holds true. So the first step is sort of treating those AN that are strictly greater than 1, and the way how to do it, it's again, I don't know. Yeah, well, let me also, for simplicity, think only when B, for example, is greater or equal than 0. So to remember that we're going to be, so we only have contribution to the negative part of the spectrum from A, it's not from B. Now, then there is a very simple inequality, which Dirk and Barry used in both ways. And then basically they reduce problem immediately using this two-side inequality. They reduce the problem to the discrete Schrodinger operator with some potential. So they take a window and then they use this operator value inequality. And then and this is it. You get A minus 1 and you get here 1 minus A. And that's sort of, you have use both of them and you get finally the result if you prove it for the discrete Schrodinger operator. We also do the same thing, and then we do exactly the same inequality for those A which are greater than 1. So and that is a sort of a treatment. We adopt this treatment from Dirk's and Barry's paper. But for the elements which AN which are less than 1, it's very different, and that's sort of what we are going to do. So. And let me explain how we do it with the elements AN less than 1. It's actually could be interesting to for some other cases, I suppose, too. So it's a more sophisticated, much more sophisticated method. So what we do is that we take a window AK, and then we have, well, I put here sort of off-diagonal, only off-diagonals elements right here. And they, I mean, it's just for me, it's convenient to make them different notation for them. So we just take this window and introduce the matrix U, which has elements 1 and minus 1. Of course, it's a unitary matrix, but it just it's a much more simple unitary matrix. It's also self-adjoint, and then so it's just 1 and -1 on the diagonals, right? But what happened if you apply this matrix and if you surround a matrix AK with this U, then this sort of magic thing happened, and all the elements would be exactly the same here, but here you get minus, right? And what we can do now, we can write the matrix AK, or this window AK, as follows. We get a, say, here we put k plus 1 divided by 2, and then here we can put 1 minus k divided by 2. Of course, if you, because of these two minuses, then of course, if you put in, you get exactly k. But what is interesting here is that k plus 1 over 2 and 1 minus k over 2, the sum of them is equal to 1. And of course, this matrix could be written as follows. It's U A prime A, where A prime is this matrix. So here we have 1, 1, here we have minus 1, 1. And of course, if you surround U A prime by U and U, then what it does, it just instead of this minus 1 and minus 1, we get plus 1 and 1, right? And that's exactly what it is. All right. So now, so what do we do then? We can repeat this process, and we can eliminate all the terms which are less below, I mean, all diagonal terms which are below 1. We can eliminate them. For example, once we have this one, we reduce our big matrix to this one, and having this constant, we can, for example, if C is greater than 1, we can do a similar thing, and then we can write it, split it, this matrix into a sum of 2. Again, of a similar type, and then having a similar structure. And then in the end, what we have is that the whole matrix A of diagonal matrix, we can sort of make all this, considering all these elements which are less than 1, finally, we write it as follows. Right, I mean, here is sort of, and also, in a way, what we also do is that we can reduce finally it's to the matrix where the all diagonal elements are equal to 1s here. But of course, those part of the matrix of matrix A that had that, well, corresponding AN greater than 1, then we move them according to step 1 to the diagonal. But whatever it is that what is important is that you have this property for these lambdas, right? So, okay. So then, of course, the eigenvalues of, yeah, I mean, this is just a remark that the eigenvalues of this matrix and this matrix are exactly the same. And there is a lemma, which sort of we need, we need a kind of, for the future, we need an equality here. And then it says the following. Suppose we have operator valued mapping. So, and then we have this condition that beta is greater than x. X is a matrix right here. And then suppose we have the beta minus x to the power minus 1. Then this operator function is operator convex. So we have operator inequality here. Right. So here we have lambda and 1 minus lambda. Sum of lambda and 1 minus lambda is equal to 1. And then we can take out lambdas outside. So sort of it's a convex, somewhat convexity. Well, it's not a very complicated inequality. Basically, finally, it reduced to something like lambda A plus 1 minus lambda to the power minus 1 is less or equal than lambda A to the power minus 1 plus 1 minus lambda. I mean, eventually you manipulate with the matrices or with operators, it doesn't matter really. And then everything is self-adjoint because we have, of course, inequality. Of course, you assume that X is self-adjoint. So in the end, you use spectral theorem. So basically, it's an equality. You reduce it inequality to the numbers. So but I don't want to prove it. It's just a simple manipulation. And what is not simple is that this mapping, this inequality, is relevant to what we are doing. Now, what we do now, as one does in this particular sort of problems, one introduces the Biermann-Schwinger operator. So that's what we have. We have a Biermann-Schwinger operator where beta is greater or equal than 2. And here, this is our A. And then what we say is that that this is a negative. Well, this is a compact operator, definitely, and it has, and we can enumerate the eigenvalues of this compact operator in a decreasing order. So what we really need in the end is that we only look at the positive part of it, actually. So and therefore we don't need at the moment we don't need we ignore the negative part, so we just take a positive part of it. So then what we do now is that we use the lemma, all right? So we have this presentation of the matrix A in the following way, right? And then what we can do, well, I mean, for example, at the moment we actually can assume that A only includes the of diagonals elements of A includes only those elements which are less than 1, A and less strictly than 1 or strictly or equal than 1, and therefore the separator would be positive, and therefore what we can do is that we use this lemma, convexity lemma, so we can take, so instead of A, we write this linear combination, which we have here, and using these inequalities, we can take lambda out. We use this convexity, and then and that's reduce our k beta to this one, where the diagonal elements are equal to 1 identically. Okay, right. So then actually, what we also need is that we introduce this multiplier. And then we shall see, and we define this operator L mu in the following way. And of course, we just write down, we just rewrite what we wrote here. Nothing happens here. We just rewrite having this linear combination, and then we reduce it to the problem with the one of diagonal, right? So the operator L. Operator L is a little bit better than the operator K here, and that's why we multiply it by this multiplied, and we see what happens in the future. So let me just make some computation, which is sort of in order to familiarize you with the discrete Schrödinger operator. We do it slowly. It's a lot of text here, but we will do it slowly. So what will happen in the future with our beta is going to be mu plus 1 divided by mu, and mu is here, mu is less than 1. That's important, right? Now, and then, well, very simple computation. If you substitute beta equal to this value, then you have this equality. Now, we can look at the matrix representation of this one. And what I claim is the matrix representation of this operator is actually equal to this one. And why is it so? So we simply compute the resolvent. This is basically A1 is a matrix which has simply off-diagonal elements and nothing in the diagonal. Off-diagonal elements equal to 1. And it's just say free resolvent, right? With a resolvent parameter mu plus n to the power minus 1. So if, for example, what we do is that to compute this resolvent is just, and that's sort of how it looks. So, for example, in order to compute, to prove that this formula is correct, then what we do, we just apply this operator to this un. And then we immediately see that if n is greater than m, n is greater than m, then what is it? This is our sort of a multiplication operator, this one, right? And then this is a shift by +1, and then shift by -1, which Jacobi, free Jacobi matrices does, not Jacobi even, but discrete Schrödinger. And then you see that it's equal to 0. If n is less than m, then we have exactly the same, but something happened when n is equal to m. And of course, we would like to have the element equal to 1, and that's sort of, that's exactly what happened here is that, so because of this modular, which appears here, when we take n on both sides from m, then instead of cancellation, instead of terms like this, we get exactly this one. And then we see that it's exactly equal to 1. So what it means is that if we now look at the matrix L mu of A1, then this is our Biermann-Schwinger matrix, right? And then this is a free resolvent, and then B surrounded by B ends, and then this coefficient, and it's exactly the same coefficient that we had here, because this is exactly the same as this one, and therefore we have a very simple form, and this is the form of the elements of the matrix here, right? Okay. So let's remember this formula. It's going to be an important formula. Now, what we do now, we just think in terms of the Fourier transform. So we introduce Fourier transform, and that is un hat equal to uk. We correspond to the sequence un hat. We correspond to the function defined on minus pi pi, and then inverse Fourier transform. And now what we do is that so of course the standard, the second derivative, the discrete second derivative, of course, it's just multiplication by -2 cosinus k. After the unitary transformation of the standard discrete derivative, second derivative. And of course, what we do now, we introduce matrix, not matrix, but the function g, which is equal to the following one. So this is exactly a resolvent, or maybe better to say fundamental solution, because of course, the resolvent you get if you take inverse Fourier, if you take inverse Fourier and then surround this one by f star and f. So, and again, you see here we have this coefficient, right? Apparently. So it's exactly the same thing, right? So that's what we get. We can correspond it, if you take Fourier transform of G mu, and there will be a sequence, and then when m is equal to 0, it's exactly resolvent, right? Resolvent when, it's exactly this one. So what is interesting is that, first of all, this is a non-negative one, right? Because so 1 divided by mu plus mu is greater than 2. Now, then, of course, from here, we immediately see that when n is equal to 0, then this function is equal to 1. Therefore, we can claim that g mu of k is a probability measure. So, and then of course, what another simple identity is the following: if we take instead of mu, we take mu, which is greater than mu, then of course we have this simple identity. We just multiply and divide by mu to the power n, And therefore, we have that G mu n can be written as a product of these two, right? Under this condition, right? So it's important that, of course, mu divided by mu is less than 1, right? That is important. And of course, if you look at on the Fourier side, then of course this product moves into the convolution, and that's what we write down. And then since you have this identity, then convolution of these two G's is equal to this expression. So that is the thing. Okay. Now, so similar to what we had in this paper with Dirk and Tima, one has this little proposition. Basically, it's a kind of Kifan inequality. So if you have a compact operator and you have eigenvalues or S numbers, whatever, then Kifan inequality said that if you take the sum of the first largest and largest eigenvalues, then it's a norm. So this is a norm. So you have a triangle inequality, and that's what we need. We need triangle inequality here, right? So if you take T1 plus T2, and then you take sum of the first n eigenvalues of T1 plus T2, then it's less or equal than the first eigenvalues, sum of the first eigenvalues of T1, and plus sum of the first eigenvalues of T2. And then, of course, you can generalize it into the following proposition, saying the following, that if it's an abstract thing, if you have T non-negative, say, compact operator, naturally self-adjoint, and G is a probability measure in on some omega, and these operators are unitary depending on K, then you can have we have this inequality, right? So it's basically a triangle inequality, right? So you put norm inside and then use the fact that V is a unitary operator. Right, okay? So how should we use it? So what we do now, we consider now introduces as mu, which is the sum of the n largest eigenvalues of this operator now. You see lambda is already outside, we don't, so by using this lemma, the convexity operator convexity lemma, and then the lemma, which we call monotonicity lemma, state the following thing, is that we take the n eigenvalues, largest eigenvalues of this compact operator, and then depending on mu, and if we increase mu, namely consider mu which are greater than mu, then we have this inequality. So the trick is the following. So what we have is that we consider, say, operator fk, which is just multiplication by just exponential function. Of course, naturally, it's a unitary operator. Just multiplication by this function. It's a unitary operator. So then what we can do, we take some, I suppose we can write here some n, which is correspond to S n mu. This one corresponds to, it's exactly S n mu. And then we simply write it down what it is. In the using this G, right? So what we have is that, as I already mentioned, this is basically a fundamental solution. And then if you surround it by the Fourier transform, that would be exactly the resolvent. And then this is exactly the Biermann-Schwinger operator. And then, yes, and then it's of course, G had this extra term, which we introduced before, namely this extra term, right? So it's sort of, and that is important. And then, and this is, so this is exactly how this L mu A1 looks like. It's exactly the same thing, right? And then we use simply that G could be written as a convolution of two, and namely G mu and G mu divided by mu. And then here we have still Fk, and then Fk star. But Fk, looking at this expression or definition of F, of course, it could be written as the product of these two, just simply canceling the exponential functions. And therefore, I mean, after substitution, k minus k prime equal to k 2 prime, we can simply rewrite it. We can take out one of the integrals, we put some with respect to j inside. No, I think it's probably not correct here. I don't think we need here n, right? Yeah. Or we just take this. Yeah, we just have operator inequality. I mean, the monotonicity lemma, right? So we assume that we have, I mean, we have representation, and then we apply the T-fan inequality. So we just continue with representation. So we have this convolution, and then we can rewrite it as follows. We can keep some of lambda j. We can put it inside, and integration with the k prime we take outside. Here we have this one and this one. And then an integration, and then function g mu divided by mu. We put it here depending on k, but k minus k prime we substitute by k2 primes, and of course we have to have this substitution. And we use here that everything is 2 pi periodic, so it doesn't really matter how we integrate from minus pi to pi, or from minus pi minus k 2 prime and k2 prime, and then that is, I think, probably there is some kind of misprint here, but maybe here I should put prime here, I suppose, right? Probably should be prime. Anyway, so what we have here is that we have this representation. So now here we have a unitary operator. I mean, multiplication by this exponential function. Here we have probability measure, and then we have this one, and therefore we can simply forget about this. If we take some of the first eigenvalues of this operator, and then it's less or equal than the sum of the first n eigenvalues of this operator, and that is how it uses. So I want to point out is that there is a kind of a, yeah, well, let me just continue a little bit. So what do we have now? So what we have now is the following. So now we introduce special news, and then we parameterize our eigenvalues, positive eigenvalues, by this sum, which is greater than 2. And of course, when mu j converges to 1, so of course mu j less than 1, and then of course they converge, decrease, these eigenvalues decrease to 0.2, right? 0.2. Now there is a very famous Bierman-Sphincter principle. So what we have is that if you consider j eigenvalues j, ej of the Bierman-Sphincter operator, then so, and when ej plus is an eigenvalue of the operator A, right? Then the eigenvalue of j eigenvalue of this operator with eigenvalue ej is equal to 1. Is exactly equal to 1. So this is equal to 1, right? You see, it's a kind of a funny thing because we consider for each j, we have a different operator here, right? Because ej's are different. And then here we consider j operator, the eigenvalue of this number j of this operator, which depends on j itself, right? Well, anyway, so this is what it is, and then what we have is that, of course, we can have this inequality. So again, we take our Jacobi matrix, and then the eigenvalues of our Jacobi matrix. These are exactly these terms which appeared when we defined the operator L, exactly this one, right? And then exactly what we can write. This is equal to 1. So, and then in order to write L mu j, we have to multiply by this number. And then, of course, what is it? It's just it's a sum of the eigenvalues, right? It's a first sum eigenvalues. Then, of course, we can have an equality. So operator A now we can reduce to operator A1 here. But having all these sums, right? Extra sums with UK and lambda K. But of course, now then the whole thing is a linear here. So we can take a lambda K outside, they're positive, and then some of them are equal to 1. And then we have this operator and UK are unitary operator. I mean, they sort of don't change spectrum. So we can write it as it is simply. And this is the sum of EJs of this new operator. So what is the difference? The difference is that before we had operator A here, right? We had operator A here, and now we have operator A1, right? So you see already from here, you see that we were able to reduce the part with the off-diagonal terms which are less than 1 to the part of the operator where diagonal terms are equal to 1 without any contribution to the diagonal, right? Basically, there is no contribution into the diagonal in some sense. But of course, it's kind of a complicated still expression because we have EJ of the operator depending on J, right? So how do we do that? And that is the most pretty part. And that's exactly what has been used in the paper, Duke paper myself, and then the paper of Tima, Tima. That is a sort of how you can use monotonicity lemma. So what you do is the following. So you take this sum, right? And that's what you want to estimate. It's exactly what happened in the previous slide. So then what you can write down is that the sum, what is it? You can split this, take, for example, take out 2 eigenvalues here, right? So this is E2 lambda mu 2, and here E1 lambda mu 1. But you know that you can increase mu 1, right? And then right here mu 2, right? Because they are sort of they are ordered like this, right? So and then we have this inequality due to monotonicity lemma, and now we can write down here E1 mu 2 and here E2 mu 2, and of course now this is a sum of 2 eigenvalues of the operator with the parameterized by mu 2, sum of 2 first eigenvalues. And then, of course, we can again, using monotonicity lemma, put here instead of mu 2, mu 3. And we can go on like this. And in the end, what we do, we can get rid of all of them. So finally, instead of having these indices EJ, EL mu j, we have EJ mu n. And mu n is fixed, right? So and then what in the end we have is that we have the sum of the eigenvalues, positive eigenvalues of this Jacobi operator is correspond to this one. So let me come to some kind of conclusions. So what do we have? We have the following thing. For the if an less than 1, then we do all these sort of things, right? And then we basically reduce our problem to the following one. Basically, in the end, we take mu n limit, say to equal to 1, for example, or if it's a finite number of eigenvalues, then we can stop at a certain point. But anyway, so we take a trace, and if you take a trace, then n is equal to m simply, and therefore what we in the end have is that we have trace b, right? So that is a part when we have, say, assume that we have a Jacobi matrix where all of diagonal elements are less or equal than 1, and then we have a diagonal b, right? So we get exactly trace b, and we have no contribution from of the diagonal elements. When and suppose if we have n greater than 1, then by using this inequality, which we had at the very beginning of the proof, then this each of this sort of part of the matrix gives you two contributions of the a minus 1, right? And therefore, you have the same thing, basically the same procedure, the same monotonicity lemma, the same thing. And then you, in the end, you get, instead of just trace b, you get extra 2 terms, namely 2 an minus 1. And that is when the case when you have an greater than 1. So finally, if you put it all together, and if you take only positive part, then you would have this inequality. And if you add the negative part, then you would have here you would have 4 instead of an minus 1 plus. So anyway, so you get this an minus 1 plus, and that basically completes the proof. So so what did we do? Let me just repeat a little bit. So we used a very special presentation of so one of the key points is that to establish this G mu, which is a probability measure. And then, so one thing, of course, when you deal with the negative, when the eigenvalues, when you deal with all diagonal elements less than 1, then of course one of them is this convexity lemma. Then we had this probability measure. And then this Kifan inequality is very simple, but then we had this monotonicity lemma. And then finally, we had this trick, how we use this monotonicity lemma. So that is sort of very, I find that this trick is very pretty. Sort of think about that you have here the eigenvalues, J eigenvalues of the operator depends on itself, depends on this parameter mu J. But monotonicity lemma can handle it. Okay, so that is the basic proof. But let me just come back to the final slide. Let me come back to the actually theorem which we proved, and then to example 2. So I just want to remind you, example 2. Let me repeat it again. So if B and all of them are identically equal to 1. And then this one is greater than 1, just one a 0 is greater than 1, all the others are equal to 1. Then we have 2 eigenvalues, right? And then what we wrote is that we had this inequality. We had this inequality like this, right? So, I mean, you can say that it's just that gives us a sharp thinking, and it because again. What we mentioned already, when can we consider this example, that when A converges to 1, then of course 1 plus 1 is equal to 2, so we get extra 2. So here we have something like extra 2. But whether it's satisfactory or not, I don't know. I mean, what is interesting is that that's what we have, right? This is what we have. And there is a new conjecture which says the following: if it's true that instead of this 4 and an minus 1 plus, we can consider this part. And of course, it's only includes only a and greater than 1, because otherwise it's. I mean, we know that that a n which are less than 1, they don't contribute to the spectrum. So the idea is that to have this one. The point here is that if this conjecture is true, which I don't know, no idea how to deal with, it was actually idea of L.Schimmer, who sort of thought that's an interesting case, because then what you do is that if you sort of use some lifting or sort of Eisenman Lieb type sort of arguments, then you can lift it to the case. Here we have basically studied the square roots of the eigenvalues. But there is another inequality of this type for discrete Jacobi matrices when you consider powers 3 over 2 distances to between E's and the continuous spectrum, involving powers not 1/2 but powers 3 over 2, and then it has interesting form which was mentioned already. I mean, you could see it from the paper of Simon and Lieb and Simon when they considered trace formula for the Jacobi matrices, and also there is another proof of L.Schimmer for that case, where there is an interesting term which has a logarithmic term, which is impossible to avoid. And then once you have this conjecture, then using Eisenman Lieb lifting, you can obtain exactly that formula, and that sort of gives you a possibility maybe to get something in between. And of course, the big challenge here is to find sharp constant or a better constant in the case when instead of 1/2 you have power 1 here, so, for example. So that is more or less what I wanted to say. Thank you very much.
Thank you very much for this talk. We have now some time for questions. If you have questions, you can either unmute yourself to ask them or write them in chat and I will relay them. I'll start with one myself. So at the end, you were mentioning how if you get this conjecture, you can use the Eisenman-Lieb method to lift this inequality to different powers. Yeah. Why is it that we cannot do the same if we with the inequality with the positive part that you have here?
Yeah, well, you have positive part, you don't get the same. You know, I mean the corresponding inequality for the Jacobi matrices when you consider power 3 over 2, the distance to the endpoints of the continuous spectrum to power 3 over 2, it's a sharp and it contains several terms. Well, I don't have them in front of me, but they sort of come with a sort of, for example, from the trace formula of Lieb and Simon. And then if you do lifting from this part, then you don't get the same expression simply, you know. And then, however, if you do it from this part, you get it. And if you see, if you look at this, what happens if you just have again this simple perturbation of this type, from example 2. Then it's quite natural to have this term rather than this one in some sense. You know, I mean, if you also look at compare it, so what you have here, you see, of course, if a_n is greater than 1, then of course 1 divided by a_n here is less than 1, right? So when you subtract more than this one, right?
Yeah.
Yeah. So in fact, this expression is bigger than this one, right? However, instead of 4, you would like to have 2. So you win here. That's the way it is.
Yeah. And am I correct in assuming that the difficulty with proving this conjecture is the fact that you cannot start with this reduction where you change all the coefficients to 1, so the computations have to be much more direct with the operator you're given rather than having this reduction that you had.
Yeah, no, in principle you can, because I mean, sort of that's what's suggested in the paper of, I mean, what they do, they vary and it can vary. What they did is that they just use this inequality, right? You know, this one.
Yeah.
And this,
yeah.
And then they immediately, and then they were concentrating the proof of the discrete Schrodinger operator, basically. And once you have this into inequality, but it's too rough. I mean, it doesn't sort of take into account that it's good only, or it's reasonably good only for those A which are greater than 1, right?
Wow.
Yeah,
Nice. Does anyone else have questions for the speaker? All right. Well, if not, thank you again for speaking today.
Okay. Thank you very much. Yeah. Thank you. Thank you for inviting me.
Yeah, you're welcome. We will reconvene next week with a talk by Steve Zeldich, who will talk to us about eigenfunction restriction problems. So see you all next week, and thanks for being here today.